All right, I'll get started. I think everybody's here. So, dear Heavenly Father, we thank you for this day. I thank you for these students. Just pray to be with us today. Help us to understand the material we go over. Help us to glorify you again, Lord, in what we do this day, Lord. In your name I pray. Amen. Okay, so got a couple more examples of Lagrange multipliers to show you. Let me get to them. This is my example 5.1.7 in my notes. Our objective function f of xy is e to the xy, and we want to find the extrema of f on the curve x cubed plus y cubed equals to 16. All right. Now, so let's go to it. The constraint is what then? Yeah, g is equal to x cubed plus y cubed, right? That's equal to 16. So our Lagrange multiplier condition is gradient of f is equal to lambda times the gradient of g. What's that look like here? Well, let's see here. We've got y e to the xy, comma x e to the xy. Why do I have a y and an x in front of the exponential? I'm differentiating e to the xy with respect to x and y, respective, right? I have to use the chain rule both times, but partial derivative with respect to x of xy spits back y. The partial derivative of x times y with respect to y spits back x. That's why there's an x here and a y there. Now that's equal to what? Lambda 3x squared 3y squared. Okay. Oftentimes if you solve for lambda, that's a successful strategy to work through the algebra. Again, I wouldn't claim to have some kind of global strategy on how to solve these. Generally speaking, you've got nonlinear equations, several variables. You know, it's kind of hard. But lambda, let's see here. We get two equations, right? If you break this out, we've got ourselves a y e to the xy equals 3 lambda x squared, and x e to the xy equals 3 lambda y squared. So if I solve both of those for lambda, I get y e to the xy over 3x squared equals to x e to the xy over 3y squared. Of course, then you can cancel the exponentials without harm, right? The exponential is never 0, so what's that give us? The 3's cancel. We get y cubed equals to x cubed, which is very nice, right? Why? Because then we can go back to the constraint, right? Go back to the constraint up here, and then we get what? 2x cubed equals to 16, which we can solve, right? What does this give us? Yeah, x cubed is equal to 8, so x is equal to 2. Now, if x is equal to 2, what's y equal to? 2, right. Y is also equal to 2 from this, I guess. Take the cube root of that. All right, so then what? So we have f of what? F of 2 is equal to what? F of 2 is equal to e to the 2 times 2. In other words, e to the 4. Right? So what could you already tell me about the constraint surface, the constraint curve, even though I haven't tried to graph it? Given that it's quite clear that this function is not constant, I mean, that's either a minimum or a maximum, most likely, right? I guess my point would be, if you don't get a min and a max, you can already kind of guess it's not a compact curve, right? Because compact curves and continuous objective functions have to give you min and maxes. So if there's not a min, if there's not two things, it stands to reason it can't possibly be a compact curve. So it's got to be like a plain example. Now, it turns out that the plot of this thing looks something like, I butchered it. It's like, it's kind of like, that's not right. It's not it at all. It's something like, and I think this point is 2, 2. So this is what x cubed plus y cubed equals to 16 looks like, something like that. Now, what happens, superimpose the xy axes. What happens as you go off this way? You have y greater than 0 and x less than 0, right? As you go that way, you've got x greater than 0, y less than 0. So in both cases, what do you have? You've got xy less than 0. You've got xy less than 0. And it gets bigger and bigger and bigger and bigger and bigger and bigger and bigger as you go further out. What happens to the exponential as you feed it increasingly large negative values? Right. So it's asymptotically going to 0, basically along this constraint. And so it stands to reason that this is in fact a global maximum. Now the reason I know that has to do with the analysis I just told you. It of course is not granted to me from the method of Lagrange multipliers in and of itself, right? I don't expect you to have memorized the plots of cubic functions, by the way. This is something I created with Wolfram Alpha. Like, I personally also would not know without work. I mean, give me 10 minutes, I can give you something, some kind of picture for a cubic. Just plug in some points and see what it does, but, that's not something that you missed in a previous class, all right? There are other things that maybe you missed in a previous class that I'm telling you, like, everybody should know, and maybe you should know too. This is not one of those things, right? This is not common knowledge that this looks like that. At least not common to my experience. Any questions? All right. Let me look at another one here. Example 10. Example 10. This is a classic example. You've got a box, and you're going to let x, y, and z be the lengths of the box, the sides of the box, all right? So x, y, z, the lengths of the sides of the box. And here's the instructions. A rectangular box without a lid is made from 12 square feet of cardboard. Find the maximum volume of such a box. So an open top box is made with 12 square feet of cardboard. Choose dimensions to maximize the volume. Now, of course, there's all kinds of variations of this, right? Like you can take one side and remove some little window or something, and there's all kinds of different stupid ways to twist this problem to make it slightly different for like a test or a quiz or something in a typical Calc 3 course, right? But this is the nicest version of this problem. Okay, so what do I do? What's my objective function here? It's the volume, right? V is like the F. And so V is equal to x, y, z. So this would be like f of x, y, z in our previous lingo. What's the constraint? Yeah.
Can we just use surface area by removing one the side?
We neglect the thickness of the cardboard. I mean, this is open, but there's every other side. There's the bottom is there, the back, right?
So it would be 2x equals 2y equals xy equals what?
Yeah, see the surface area, you say you got 2xz plus 2yz plus what?
xy.
Just xy
Because it's
is equal to 12. Does everybody see how he did that? You do know that x times y would be the area of the bottom of the box. For you, it's insulting. For other classes I teach, it's a helpful comment. Sorry. It's true. It's true. Reality is cruel sometimes. What can I tell you? So there's our constraint. And there we go. So now, off to the races, Lagrange multiplier. So what do we got? The gradient of the objective function is equal to lambda times the gradient of the surface area function, right? What's that give me? That gives me yz, xz, xy is equal to lambda times 2z plus y, calculating, 2z plus x, 2x plus 2y. Very good. All right. So what do we face here? We face yz is equal to lambda times 2z plus y. Xz is equal to lambda times 2z plus x. And xy is equal to lambda times 2x, well, 2 lambda times x plus y, let's say. I probably should put the 2 in there. I'll make up. Oh no, look what I've done. When I see equations like this, you know what they say to me? They yell at me, make me look the same. So like, you know, how do you make those equations? Oh, I don't do that. Huh. No, I do that. So this is lambda times 2x plus 2y. So what do? My next move is to make everything easy to match up. I just multiply each one by what's not there. So the first one I multiply by x, the second one I multiply by y, the third one I multiply by z, which gives me xyz, xyz, xyz. So xyz is equal to lambda times 2xz plus xy. xyz is equal to lambda times 2yz plus xy. xyz is equal to lambda times 2xz plus 2yz. That's kind of made the equation symmetric now, right? Now you can equate them, right? Let me call this 1, 2, 3. Put them together. So divide by lambda, right? What does that give you? 2xz plus xy is equal to 2yz plus xy is equal to 2xz plus 2xy. Then what? Square them?
Sir,
Yeah?
number 3, shouldn't that be 2yz, not 2xy?
Oh, yeah, thank you. Anything else? So I can extract a couple of simpler equations from these, right? I can look at this bit here, and that gives me what? It gives me xz is equal to yz, because the xy's cancel. And then over here, I get what? The 2yz's cancel, and I get xy is 2xz. Is it safe to divide by variables here? What is the meaning of x, y, and z? Do we lose anything interesting when we divide by x, y, and z in this problem? No, we don't. These are lengths of a, these are dimensions of a box. So if there's some solution that has one of those being 0, it's just some sort of mathematical artifact that we don't care about anyway. So there you go. This gives us what? X equals to y. And this gives me what? Y is equal to 2z. So now we can go back to the surface area. What do we get? Which variable do we want to keep? X is equal to y, but y is equal to 2z, right? So we can put everything, we can make all z's, right? Make everything z. So I have 2 times 2z times z plus 2 times y, but y is 2z times z plus x times y, which is 2z times 2z, right? All of that's equal to 12. How many z's do we have? We've got a z squared, right? Z squared times what? 4, 8, 12, right? So therefore, z is equal to plus or minus 1, but of course we want 1. And once you know z is equal to 1, that tells me that x is equal to 2 and y is equal to 2. So the dimensions are 2 by 2, 2, what are we using? Feet. 2 feet by 2 feet by 1 foot is the box that you want. And you can easily check the answer. You've got a 4 square foot base, and then you've got 2 feet, 2 feet, 2 feet, 2 feet, 2 feet, right? Yeah, 4 plus 8 is 12. This is a pretty standard example. People usually give this one. Any questions? Yeah, there doesn't seem to be a minimum volume here.
So that is the maximum, because you can make a different box with 12 feet, but.
That's the maximum volume.
Yeah, so this is the maximum, so then
Yeah.
there's no way to find it with this information.
I don't.
You don't need to do this to find the minimum. You set one of them equal to 0, the other two are just square root of 12.
Well. Oh, yeah. I think Mike is right. He's saying you just make the base 12 square feet, and make the height 0. Yeah. I was thinking of something much more complicated. I was thinking of like something infinite, but infinitely thin. But that's what you're saying also. Sorry.
Would it be cube versus flat?
Depends on your definition.
It's a degenerate. It's a degenerate box. In that the minimum volume's a degenerate box. Yeah. I mean, if you have some solid that has 0 volume, it's not really a genuine solid, right? Well, unless you're a mathematician and you like doing weird things with volume. But anyway, that is for another course and another time. Now, so these are your standard examples. Now over here, I set my sights on something harder. Here, what I'm looking at is the question, here's a quadratic form. This is my objective, is to take this arbitrary quadratic form and to find its extremal values on the unit circle. So the unit circle, x squared plus y squared equals to 1. I want to maximize or minimize the quadratic form on the unit circle. And I want to do it for an arbitrary quadratic form. Why do I want to do that? Because of what we're about to do. This provides the sort of the base ground floor thinking for our second derivative test. All right? So I need this example of examples as a theoretical basis for our second derivative test. All right, that's why this is here. Of course, this is a little bit harder than what we just did, but I just want to walk you through it here. So if this is the quadratic form, I can rewrite it as a row vector times a 2 by 2 matrix times a column vector. All of you will take 221 or 321, so at some point soon you'll need to know this. It's harmless. It's just you don't know it yet, maybe. Anyway, so quadratic form is really just something that's a sum of squares, or at least order 2 things, all right? It's quadratic because each piece has order 2. Now, if I look at the Lagrange multiplier condition, that would be the gradient of the quadratic form, gradient of q, is equal to lambda times the gradient of g, where g is the unit circle equation, right? Now, when I write that out in terms of dot products of r and ar, where r is just the vector xy, it looks like this. Now, at this point, I realized, I need some little identities to work through this. So what I did was I figured out if I take the gradient of a dot product, I can rewrite it as a particular linear combination of partial derivatives of the vector, like this. See, the gradient of a dot product of a and b is actually equal to x hat partial a partial x dot b plus a partial b partial x plus y hat partial a partial y dot b plus a partial b partial y by this little calculation right here. That's an identity. Now, when you consider the partial derivatives with respect to x of AR, since A is a constant matrix, you can pull the partial derivative past the matrix multiplication. And what's partial r partial x? Well, partial r partial x is just the x hat vector. And if you multiply a matrix by the x hat vector, it just picks off the first column. That's the way it works. If you multiply a matrix by the y hat vector, it picks off the second column. That's the way that works. Now the second column, BC. First column AB, second column BC. And so these are nuts and bolts. I need to come back over here and study the Lagrange multiplier equation. So the Lagrange multiplier equation, this breaks down to that with the identity I just mentioned. But when I flesh out what this is, this term gives me ax plus by. This term also gives me x comma y dot ab, which is ax plus by. So I get 2 copies of ax plus by from this first term. I get 2 copies of bx plus dy from the second term for much the same reasons. So when I collect that all together, I have twice ax plus by, twice bx plus dy in the x hat and y hat component respectively. And you can rewrite this as a matrix equation, a, b, c, d times x, y. And on the other side, really cool things happen too. X partial r partial x is x hat dot r is just x. This is also just x, so I get 2x, x hat. Over here I get 2y, y hat. In short, I get twice the vector. And so we come to this equation, and once the dust settles, the Lagrange multiplier condition simply becomes AR is equal to lambda r. This equation I have boxed means that R is an eigenvector with eigenvalue lambda. But the really cool thing about this calculation is that because the unit circle is a compact constraint curve, I know that this quadratic form attains its minimum and maximum values on the unit circle. Consequently, this lambda that we're looking at has to be a real scalar, has to be a positive or negative real number. And so this actually proves that a 2 by 2 symmetric matrix has a pair of real eigenvalues and eigenvectors. Now, in linear algebra, you'll study this equation extensively for a couple weeks. It's an important chapter in linear algebra. And so that's really the right place to tear this apart and to understand why this breaks down as it does. In my notes, I give a completely unlinear algebraic proof of what I'm about to show you. In my notes, I take about 3 pages to derive essentially this condition in disguise without using matrices, without using vectors essentially, just hand-to-hand combat with equations, and eventually I come to the following theorem I'll show you. And that theorem I already quoted for you once before when we came across that example that had the mixed term in it. Remember, it had the cross term in it. I said, fun fact, here's how the quadratic form breaks down. Well, this is how to derive that. So I'm about to talk about theorem 5.1.13 on page 251. Well, I don't know if it's on your page 251. I may have reformatted. It's around page 251. And again, we need these results to prepare for what we're going to do a little bit later in our discussion of optimization, all right? Won't be long, though. Maybe even today. Depends on how much time I spent working out these first examples. Come on. You could do it. You could do it. Yeah. Here is theorem 5.1.5.13. So, if we study the quadratic form ax squared plus bxy plus 2bxy plus cy squared, here a, b, and c are constants, all right, given constants, then the graph can look like a couple different things. So the lambda, it turns out, has to be the solution to something called the characteristic equation. You calculate the determinant of a minus lambda I, which is the determinant of a minus lambda, b, c minus lambda. You set that equal to 0. The solutions to this so-called characteristic equation we call lambda 1 and lambda 2. They have to be real values because of the argument I just ran through over there. And these are the different cases you get. You can get both eigenvalues positive. That means that there's some system of coordinates where it looks like a paraboloid. It looks like z equals to x squared plus y squared. So it's at a minimum. The 0, 0 is at a minimum if both of the eigenvalues are positive. If both the eigenvalues are negative, it looks like it's like something like a paraboloid that opens down. So it's like a maximum. If one is positive, What? Oh, if this is saying that one's positive, one's negative, right? Then it's like a saddle. It's something like a hyperboloid. Now, the way you get to that is you have to rotate from xy coordinates to, say, x bar, y bar coordinates. There's some rotation that removes the xy term, so that when you have x bar, y bar, you just have like lambda 1 x bar squared plus lambda 2 y bar squared is the formula for q in that new coordinate system. These things we go into great detail in linear algebra. The other two cases are you could have one of the eigenvalues with 0 and the other one's either positive or negative. In that case, the graph, if you looked at like z equal to q of xy, you'd have like a parabolic trough, either opening up or down. So these are the different things that can happen with the different possible things that can happen with an expression like that. All right? Yes, sir.
The lambdas in the right characteristic equation, the first one, lambda 1, second one, lambda 2.
No, well, it's like ax squared plus bx plus c. Lambda is a variable, so the solution to that would be lambda 1 and lambda 2. But you have to be able to put lambda 1 both places and have it work to have it be a solution. You know, it's the variable lambda versus the solution lambda. We use lambda for both. What's that?
You're just comparing them with each other and zero.
Yeah, I'm comparing the solution set. I'm talking about the solution set to that equation in these different cases. Now, it turns out, as we go on here, the only thing that really matters to us is cases 1, 2, and 3. That will turn out to provide the basis, actually, for what's known as the second derivative test. All right? So I want to do this now so we have it as a backdrop to explain why that's true. Yep.
What is an eigenvalue?
Well, an eigenvalue, you have a matrix. If you can find a vector that when you multiply the matrix times the vector, you just get back this number, lambda, times the vector again, that makes lambda an eigenvalue. It's so an eigenvalue is paired with some kind of special vector that when you multiply that vector on the matrix, it's very boring. It just takes the vector and spits it back at you, stretched out or compressed in a certain direction. So they're really special kinds of vectors, and the corresponding values that tell you the scale factors associated with that, those are the eigenvalues. Geometrically, what's going on is basically this. If you have, what we're really talking about is something like, could be like this. This could be something like, ax squared plus 2bxy plus cy squared equals to 1. All right? It could be an ellipse. And what these eigenvectors are actually going to be are the principal axes of symmetry. So these would be like the eigenvectors, these directions. And that lambda 1 and lambda 2 has something to do with like the length of the semi-major axes and semi-minor axes. That's the geometric meaning of it. But that's not calculus 3, but it's fun. All right. Again, this is just a necessary evil for us to understand the second derivative. A necessary awesomeness for us to understand the second derivative test shortly. So, with that, I shall move on. So here's some things I don't want to write all of these out, but I will. Do you remember these? They're back. Yep. The whirlwind is coming. It's time for you to reap it. Yes. Glorious power series. We will come back to the quadratic form thing in due time. Now, I'm going to talk to you about multivariate power series. Go away. I said go away. So again, just to go back to my big picture comment here for a second. The big picture is that we're trying to optimize functions of several variables over some domain of consideration, right? Now, Lagrange multipliers is awesome for boundaries, right? It does a great job there, but it doesn't really tell you about what's in the box, right? I mean, the edge is great, but it doesn't tell you about interior points. And so this theory of multivariate power series, multivariate Taylor, is going to give us the tool we need to tackle that question. So what is the multivariate Taylor series? If I have a function of two variables, here's what it looks like. Now, we've already talked about a lot of this. What are the first three terms? Yeah. This is the linearization, the graph of which is the tangent plane, right? This is the linearization of f of xy centered where? AB. What's the next piece? This next piece is the so-called Hessian. Sometimes it's called the Hessian. Sometimes the Hessian is reserved for the matrix that corresponds to this. But you see, I could rewrite this as fxx, fxy, fxy, fyy, times what? Times x minus a, comma, y minus b times this. And so I usually just refer to this whole piece as like Q for quadratic. It's the quadratic piece of the multivariate power expansion. So what does the function look like if we have a critical point? What's a critical point? These are, I have neglected. I get tired of writing this, but I guess it's important. It's at that point, right? So a critical point, by definition, critical point has the gradient of f at that point equal to 0. Right? So look at this. Just what do we have then at a critical point? How's the function behave? So at a critical point, what do we have? We have f of xy equals to what? F of AB, right? And then the fx and the fy terms are not even there. What's the next thing? The Hessian, right? Which I'll just write as Q. Okay, so plus Q. Fine, I guess it has an x and a y dependence. I don't know, whatever. Right, and then plus stuff. Now, if you're close to the critical point, thing about the stuff in the plus dot 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 is it depends on like cubes or fourth powers or fifth powers or even higher powers of x minus a and y minus b, right? So what happens to x minus a and y minus b if you're really close to the point? You know, if this is the point a comma b, right? And if this distance is, say, distance 1 from there, if you look at, you know, this point, x minus a comma y minus b, x comma y, right? Then the displacement vector from the center to that point is the x minus a, right? This is x minus a, y minus b, right? Both of those things are less than 1, right? X minus a, the absolute value of x minus a is less than 1. Absolute value of y minus b is less than 1. If you're really close to the point and you start looking, what's the difference? And so think about what if it's 0.1? 0.1 squared is what? 1/100th. What's 0.1 cubed? 1/1000th. What's 0.1 to the fourth power? You get the idea. So which term dominates close to the critical point? Which term in the power series totally dwarfs anything else that's there? The hash, yeah, this piece right here, right? And so how do you figure out what that looks like? See, because generically speaking, it's some kind of quadratic form. It's got a mixed term, right? Mixed terms are hard to understand. Except that they're not, because I just showed you the theorem which totally breaks down how to understand what the mixed term actually looks like. All right, this will lead us to the careful statement of the second derivative test in a future lecture. I'm going to let this percolate in your mind and we'll come back to it, okay? So, I know you guys are kind of anxious to actually see some actually honest to goodness power theory calculations, right? I know you're like, yes, finally, I've been missing them. And I'm so happy that I get to do more. Yes, no? Now, I hope one of the things you picked up on in Calculus 2 was that while it is good to know the Taylor series, it is often not good to use it directly, right? Using the Taylor series directly when you could use a substitution instead is grossly inefficient, right? So there's some standard results we need for series. So a couple. I'm introducing this here, right? We're not done with this yet. First of all, I need to prove that that's actually true. We'll do that in a future lecture, okay? Another thing I need to show you is the actual statement of the second derivative test. I've sketched for you the intuition of it today, right? Again, we'll come back. But before we do that, I want you to get a better sense of what we're doing in terms of the calculation. So let's look at some standard results. Let's see here. How about this? 1 over 1 minus u, what's that equal to? E to the u, what's that equal to? Sine of u, what's that equal to? What's sinh of u equal to? What's cosine of u equal to? What's the cosh of u equal to? Here, we're primarily interested in finding expansions to order 2, for the most part. So, yeah, I could write down like the summation notation formulation of these things. But pretty much if we have the first 3 terms, it'll suffice for most of the calculations we're interested in. So this is the what? Oh no. You guys don't recognize? Yes, geometric. So what is this? This is what, 1 plus u squared plus dot, 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 right? That minus is important. How about e to the u? 1 plus u plus 1/2 u squared plus 1 over 3 factorial u cubed plus 1 over 4. Again, I don't need all these, but I'm just doing them for a reason here. Sine of u is what? U minus 1/6 u cubed. Well, fine, I'll do 3 factorial just to keep the pattern here, plus 1 over 5 factorial u to the 5th plus da da da. Again, I don't really usually need all of that. What's the cinch? The same terms with pluses, all pluses. You see, the cinch is simply the odd piece of the exponential function. So if you add cinch and cosh, you get back exponential, right? So what's left in the if e to the u is equal to the cinch plus the cosh, that's true. That's an identity. So what does it have to be? Once you know this and that, it forces you to say what is cosh of u equal to? Right, which are 1 plus 1 over 2 factorial u squared plus 1 over 4 factorial u to the 4th plus da 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 da. And the cosine is just the same but alternating, right? So it's 1 minus 1 over 2 factorial u squared plus 1 over 4 factorial u to the 4th plus da 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 da. Of course, there are more of these to know, but these to me are the essentials. Now, the analysis is really very forgiving here, in the sense that you can do things with these that are just intuitively natural. Let me show you some examples of that. So there's nothing too really surprising about multivariate power series in the sense of how you construct them. So let me show you an example. If I want to find if I have f of x, right, and it's equal to e to the x times sine to the y, right? If I want to find the multivariate power series for that, what I can do, it's really, really simple. I just write down the single variate power series for each and multiply. I don't care about the whole thing. I'm really just interested up to the Hessian. Okay, so I'll just keep terms up the quadratic order. What is there? I've already written too much. I mean, I'm going to write it down, but I don't really need to, right? Because that's cubic, and there's no way you can multiply it by something over here and make it less than third order. So what are the second order terms here? We got a y, right? Plus what? Plus xy. And I think that's it. Now here I'm looking at the expansion about 0, 0, right? And I'll stick with that for a little bit here until you're a little bit more comfortable. Any questions about this? Yeah. Oh, yes, thank you. Excellent, excellent question. When do we end? 5:30? Oh, 5, okay. 4:30, ha ha ha, funny. All right, see here. How about, what if we had something like this? F of xy equals to 1 plus x squared times e to the y. So let's see here. We got 1 plus x squared times 1 plus y plus 1/2 y squared. What survives of this up to second order? I got a 1, right? Is there any linear term? Yep, there's that y. I think that's it for linear terms here, right? How about quadratic terms? Ooh, there's an x squared. And then what else? Oh, plus 1/2 y squared, right? I'm going to keep doing these for the rest of the class until you're totally bored with it. But in the middle of that, I'm going to do some analysis. So, what can I read from this in terms of derivatives at 0? What's this tell me? This tells me I can read right from this by comparing this to that expression with a and b equal to 0, right? So if you look at this, this would be equal to f of 0, 0 plus fx of 0, 0 times x plus fy of 0, 0 times y plus 1/2 fxx at 0, 0 x squared, etc. All right? So if you compare these, what does this tell you? What's f of 0, 0? It's 0. Of course, that's not hard to see from the original formula as well, but my point is you can read it directly from the series, you know? In fact, if I give you the power series expansion for the function, I don't need to even give you a formula for the function. The power series gives you information about the function at a particular point, all the information you need. F of 0, 0, 0, what's the x derivative? Where's the x term? It's like my solid state physics teacher said in grad school. He said, you know, elephants, they have wings. And we're like, what? And he's like, yes, they are just set to 0. In the same way, this is 0, because there is no x term. Okay. Now, what's fy? One, right? I mean, that's not terribly impressive because, of course, you could calculate partial f, partial y. What would you get? E to the x cosine of y, right? So if you plug in 0, you get what? 1. But, I mean, 0, 0, you get 1 times 1, which is 1. But I'm trying to point out to you, I'm reading them from this. What is fxy? Also equal to 1, yeah. Look at this one down here. What's this have? This has f of 0, 0 equals to 1. F sub y of 0, 0 equal to what? 1. Now, let's see if I can get you guys. fxx equals 0 equal to what? The thing I haven't proved yet, this multivariate Taylor expansion, is that there's a half there, right? So if I have a half times something equals to 1, that something has to be 2. So the xx derivative is 2. And what's the, likewise, fyy derivative is what? It's 1. Do either of these examples have a critical point at 0, 0? No, right? Because we either have we have fy is equal to 1 in each, don't we? How could I make the second example have a critical point at 0? What could I do to it? Or the first one, for that matter. How about this? Let's say g of xy equals to 1 plus x squared e to the y minus y. I just subtracted y, right? What does that do? That leaves you with 1 plus x squared plus 1/2 y squared, right? Plus dot, 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 dot. I claim it is intuitively obvious that g of 0, 0 equals to 1 is a local blank. Because if we look at z equals to g of xy now, what is it? Right, it's an elliptical paraboloid. It clearly opens up. So this is a relative what? A local what? Minimum. Just like in calculus 1, you have that kind of, but I thought it's positive, so it should be a maximum. No. Positive things next to squares give you minimums, right? In fact, by the way, guys, if you go back to calculus 1, yeah.
Well, I'm sorry, I'm kind of cutting you off midstream. I guess I'm still kind of confused on like how do you know where to stop when you're doing like the Taylor series, like and you're multiplying them through.
Oh, well, and I mean, we can ask the same question about ordinary Taylor series. How do you know how many terms to take, right? It depends on what you're doing. If we're just analyzing is the critical point a minimum or maximum, right, then I can hope that the Hessian terms non-degenerate, like, in other words, that the eigenvalues are, if the eigenvalues are 0, actually what we're doing breaks down. I can't tell. I would actually have to look at third order stuff to figure out if it's minimized or maximized. So the reason I only need to look at second order is because I'm interested in the question of optimization, right? I'm trying to figure out, given a critical point, is it, the value of the function there, is that the largest? Is it the smallest? What's the deal? Is it a saddle point? And I can see that by just looking at the quadratic terms. Like this one, I can see that 1 is apparently a local minimum. Everything beyond this is cubic, right? So that means if you have x and y close to 0, they're negligible. This is totally the shape of this close to that point. It's the best quadratic approximation to the graph. That's what the Hessian gives us. Linearization plus Hessian gives you the best quadratic approximation to a graph of two variables, function two variables. Yeah.
So the Hessian terms will always have two variables or less.
Ah, well.
You won't have x squared y or something like that.
Well, here's the reason we didn't have to do all this. I won't have x squared y because that would be cubic. So I only need up the quadratic, so just two letters. Because the third order term is like a thousandth when this is 100th. It's much, much smaller. So if you zoom in on the point, which is the notion of a local maximum or minimum, is that as you get closer and closer and closer, if you look at the microscopic behavior, basically, of the graph, that's what we're interested in when we talk about local extrema. So those higher terms can be neglected. Because we can always go closer and closer and make the things which are larger, which again are like a thousandth or a 10,000th or a 100,000th compared to just a 100th. If you're just 0.1 from the critical point, they're very small, so we can neglect them.
So do we always do the quadratic, or does it?
Well, there is no, as far as I know, nice theory for cubic terms. There's something special about quadratic things because you can write them in terms of a matrix in two variables, like sandwich between two things multiplied. There's nothing so pleasant for cubic things.
So you're saying just to repeat and know that I understand this. You're saying that the cubic terms don't matter because it's kind of like the function is exponentially weighted, and those ones are so minimally weighted that they don't impact the overall.
Right. That's essentially what the second derivative test says. And it's the same with calculus 1. If you look at a critical point, right, what does the Taylor expansion look like at a critical point? It would look like this. F of x is equal to f of a plus 1/2 f prime prime of a, x minus a quantity squared, right, plus 1/3 factorial f prime 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 of a times x minus a quantity cubed, plus 1/4 factorial f to the fourth derivative a times x minus a to the fourth plus dot dot dot.